Swayam Prabha. Digital India. Educated India.
Welcome back. After having learned the basics of predicate calculus, today we are going to start predicate semantics. So, as we saw in the previous sessions, that every semantic model has got two parts. The first part is kind of an artificial language, and the second part is a small natural language. So, it is just a fragment of the English language, the second part. Today, I hope we can just talk about a few rules of the first part, that is L1, which is an artificial language. We cannot perhaps go to the natural language counterpart of it, but we need to do the artificial language today. So, as usual, we have the syntactic rules first. So, like the old model, the old artificial language, you remember we did L0, that was our first artificial model. So, for them it is going like this, and then their natural counterparts are L0E, which we did, and after doing this we will do L1E, then something else, then L type will come here. So, and then here we should have L type E. This is how it goes on. So, in this semantic system, whatever. Now, we will see how this works. So, there are four names like L0. They are D, N, J, and M. And additionally, we have individual variables that can take only individuals. That is the reason this is first order semantics. This is first order logic. Why? Because in this logic or in this semantics, a variable like x or y can only take names. That is, they can only take objects. They cannot take predicates. So, predicates here are all constants. So, M, B, K, L, these are all constants. We do not have anything like, I do not know, like P or phi to, we do not have anything that works as predicate constants. If we had, then it would be a higher order logic. Since we do not have such things, that is, since we do not have predicate constants, this is first order logic. But that is fine. After learning the first order semantics, we can all the time go to the higher order semantics. Ideally, we should have an individual supply of variables. So, ideally we should have V1, V2, V3 through Vn, which is as I said an infinite supply, but then it will be inconvenient and complex, more complex than it is now. So, we just conveniently use 3 variables x, y, z. If we wanted to have more variables, then we would actually use V1 through Vn. So, then we have 2 1 plus predicates as we have seen before, and 2 2 plus predicates. Formation rules are given here. The first formation rule, the syntactic rules are now our main concern. Then we will see their semantic counterparts. So, the first formation rule is, if delta is a 1 plus predicate and alpha a term, then delta alpha is a formula. So to say, that is, delta alpha is a licensed construction. You can have delta alpha, you cannot have alpha delta. So, delta we can take, so delta can be any one plus predicate. So delta can be this, and alpha can be a term. So what is a term? Either an individual name or an individual variable is a term. These are all terms. These are all terms. So we can choose a name. So delta alpha can be something like M D or B X. So both are terms. I have taken one term, that is one individual thing, either variable or constant, and one place predicate. So I can actually make many different formulae by using this rule. So what is banned is you cannot have something like DM. This is banned. So it is not allowed to make anything like this, but these are fine. Then we go to the next page, and here we have, if gamma is a 2 place predicate, so we have two 2 place predicates, K and L. So if gamma is 1, and if alpha and beta are terms, that is if they are individual objects, then gamma alpha beta is a formula. So following this, you can have K, D, N. Remember, we have 4 names, D, N, J, and M. So, or you can have K, X, Y, or you can have K, X, D. So as long as you take a term, anything is fine. So all these are formulae in our system, and then if phi and xi are both formulae or both formulas, then so are 3, 4, 5, 6, 7. So we can construct then following this rule. If this is a formula, we can have another one, say, and the formula could be MX. So and we just take this one, anything. So since both MX and KXD are formulae, you can construct by using the first rule of this set, that is rule 3. Because MX is a formulae, you can have neg MX. Now I directly apply it to MX. I can also apply it indirectly, that is, after applying some other rule, I can apply this. So I can have something like MX and KXD. What is the rule I used here? I used 4. Because MX is a formula and KXD is a formula, I can have another formula which is MX and KXD, and then because this is a formula, I can now use neg and I can make it this. So this too is a formula. So by the same token, I can extend this rule. I can have anything. I can have KXD implies MX, or I can then negate it. I can do anything. What I cannot do is this. I cannot write because no rule, no syntactic rule allows us to have a construction like this. Either it will be like this. Even saying this is not possible because this needs 2 things. It must have something before here also. This is fine, but just this is not fine. This is not fine. So these are the things we understand from these syntactic rules, and also we understand that these are pretty intuitive. Okay, then we go to the next section. We have all these things. So the point is, if rule number 8, if phi is a formula and u a variable, then all u phi is a formula. We know the meaning of all u phi, which we have seen in the previous session, all u phi. we need to see how this rule works. So, I construct a formula by using it. Suppose I construct k x y. If this is a formula, it is a formula, then I can all the time use if u is a variable. So, x is a variable, this is a formula then. And if phi is a formula and u is a variable, then so is some u, my u goes to x or y or z, this also is a formula. So, these are all formulas. Now, if this is a formula, I can anytime add this, this also is a formula. So, all these are formulae. So, all these are formulae, because this much. So, this first, this is a formula. So, this is a formula, because this is a formula, this too is a formula. So, we can have all these varieties by using the syntactic rules we have here. And some very simple translations also can be done by using this language. For example, if we translate, if we interpret, if we just say that a small interpretational thing, if we just say that M is man, how do I say? I just say that M alpha means alpha is a man. And we have another one plus predicate, we have B. Suppose B means B alpha means alpha is a bat, and then intuitively K alpha beta means alpha knows beta, and L alpha beta may mean that alpha likes beta. Suppose this is how we interpret. If we do it, then we can translate a few things. We just need to see how this is a tool for understanding our natural language in a symbolic manner, in a symbolic rule guided manner. So, that is the reason we try some translations, and we also justify our translations by using the syntactic rules given here. For example, I want to say that some man likes all bats, or some man likes every bat. How do I translate? My sentence is some man likes every bat. Can I translate it? I translate it this way. First of all, man should be translated. So, how do I do it? There is some x such that x is a man, and if anything is a bat, then x likes y. Now, this is how we translate this. And then what about some man likes some bat? So, some man likes some bat. It will be there is some x such that x is a man, and there exists a y such that y is a bat, and L x y. Notice I am not saying that I am not saying y x, because the point is this x which is a man likes y which is a bat, right. So, this is how now we translate things, and also we can look at the constructions of our symbolic sentences. We can check whether these are formed properly. Now, it is very easy to check. For example, we start here. LXY is definitely grammatically correct, because L is a two-place predicate, X and Y are individual variables. So, they can combine. L requires two variables, since it is a two-place predicate. This is fine. Is BY fine? Of course, because B is a one-place predicate and Y is an individual variable. So, they unite and then you have BY. Because this is a formula and also this is a formula, this implies this is also a formula. So, we have justified this much. So, what is the rule we used here? We have used, so the first rule here is rule number 2. Then we have used rule number 1 for using this. After that, here we have used rule number 6, this rule, that if both phi and xi are formulas, then so is phi implies xi. And then we use rule number 8 for constructing this. So, we are just saying that, so we have seen that by implies Lxy is a formula. If it is a formula, then so is all y, because y is a variable. So, by using rule number 8 we can construct this, and then by using once again rule number R1, that is first rule, we can construct this. This is a one place predicate and this is an individual variable. So, they are combinable through and then, so this is combinable, and then because this is a licensed construction and this too is a licensed construction, I use now rule 4 for constructing this. And finally, because this is the entire thing is a licensed construction, I can just use rule 9 on it. So, basically we are using almost all rules. We are not using the OR rule here, we did not have OR, and we did not have this one. These two rules we did not use, but not using rules is not the point. The point is you can construct this thing, this formula. So, yeah, I forgot to write, the entire thing is R9. So, we have used in steps, we have used R1, R2 here, then R6 and then R8 and then R1 and then R4 and then R9. This is how we constructed it in different steps. Remember that there is kind of a hierarchy, not that every rule can be used everywhere. There are, for example, if I do not construct a formula, then I cannot construct some x that formula, because a non-formula will not combine. So, first I have to use rule number 1 or 2. After using 1 or 2, these are basic rules. So, after using 1 or 2, I can now go to, I can either directly go there, that is I can directly use 8 or 9. So, for example, for all x bx, that is everything is a bat, all x bx, I directly use rule 8 on so first I use rule 1, then I use rule 8 on my construction for making this. So, you can either skip this entire section or you can use things in this. So, there is an order, definitely. The order is first you have to use rule 1 and 2 and then other rules. You may or may not use all other rules or some other rules, but you have to use some rules to have complex constructions. So, this is what we have here, and then we go to the semantic part. This is slightly tricky. It is at least not as straightforward as the previous things we have seen, because we have variables here. Variables are actually difficult things, very difficult things to handle, and although people used variables previously, they used variables everywhere in mathematics or in physics or in logic. They did not theorize the use of variables. The most important person to theorize the use of a variable was definitely Alfred Tarski. He created kind of a framework to talk about variables, to actually investigate into the nature of variables. The semantic systems we are using actually use the Tarskian ideas. Everywhere it is not explicit, but definitely all are based on Tarskian ideas. We have to learn a lot of things about variables. We haven't in the sense, we perhaps know how to use variables, but we do not know how they actually function. Okay. So, the semantic values of each and every variable. If u is an individual variable of L1, then the reference of u with respect to m g, we'll know about g later, is whatever g assigns to u. We do not know g right now. So, for variables there is a function called g, a function that assigns meanings, denotations or values to variables, and there is another function, the known function f, for constants. Now, we will see f very shortly. If alpha is a non-logical constant of L1, then its meaning, its reference is given in our text. So, there is no problem. The index, that is m comma g, is very important. We will learn about it little later, not now. So, truth conditions for formulas of L1 relative to m and g. So, now we will see these. Remember the first rule, that is, which combines m and d, or which combines m and x. So, the rule about the 1 plus predicate, if m d is a construction, then what will be the reference of m d? The reference of m d will be, as they have given here, the reference of m with the reference of d. But so that is what they have said. They have said that if when m is a delta and d is an alpha, it will be denotation of delta and denotation of alpha, but it is not an ordinary combination, it is a functional combination. Here alpha is given to delta as an argument. So, this shows that this part is the argument part, this is the function takes the argument. So, this is the first thing, the first law. What is the second law? The second syntactic law was about 2 plus predicates, by using which we can make L D J or L X Y. We remember. Now, if we have these 2 plus predicates, then when this is delta and these are alpha and beta, what happens? Now, in this case, we have seen, once again we need to look back what we did previously. Once again, if you have a sentence like S goes to N and VP, then VP goes to V, T and N. You remember the syntax we did yesterday, and if this goes to VT goes to say likes, and N goes to say Sadie, and N goes to Hank. In this case, you see the combination is like this. The object first unites with the VT or the 2 plus predicate, and then this thing, this combination takes the subject. So, the order, although the order in language is alpha beta, the order of the functional feedment is beta alpha, because beta first combines or first unites with the 2 plus predicate. So, it is always beta alpha. So, alpha beta is our linguistic order, but beta alpha is our functional order. So, for the function will take first beta and then alpha, right. So, we understand. So, likes will take the object of liking first, that is Hank, and then it will take the liker or the subject, that is Sadie in this case. We have to keep this in mind while talking about all these things. Anyway, so once again we stick to this example and see what happens. So, rule number 2 states that if gamma is a 2 plus predicates and alpha and beta are terms, then the meaning of gamma alpha beta, which is we have taken x, say dj, we have taken this with respect to m and g. We will see this why m and g both is. So, there are 2 steps. In the first thing, first the denotation of L with respect to m, this is, as I said, we have to have this, takes the second thing beta, which in our case is j, the denotation of j with respect to m g, and then that function takes another argument, which is the denotation of d, the subject with respect to m and g. Then it will give you some meaning. So, as I said, the reverse order all the time comes here. That is the reason it is slightly tricky every time, because our intuitive understanding is different, but then we do not apply the intuition every time. Then the semantics part, the semantics of logical constants. If phi is the formula, then the denotation of the formula neg phi with respect to mg is 1, if and only if phi, the denotation of phi with respect to mg is 0. Otherwise, it is 0. So, what does it say? For example, I do not know whether D likes J. We do not know whether D likes J, but the point is, if this is true, suppose this is true, suppose this is 1, we just assume that this is 1, then what will be the denotation of neg L D J? It will be, of course, with respect to m and g, it will be 0, because this changes the truth value. A very important thing we need to understand all the time, because the negation always changes the truth value. If the truth value is 1, it becomes 0 when you apply the negation, and if it is 0, it becomes 1. Okay, so we go to the next page. Similarly, for all these things. Why this is similarly? Because we know the semantics of it. We have already seen the usage of this. So, we may just look back once again, just revisit the rules we did already. So, actually alpha, sorry, phi and xi, for example. So, if the denotation of phi, suppose, is 1 and say the denotation of xi is 0, what will happen? In that case, the denotation of phi and xi with respect to mg, of course, I forgot to add, we have to add this every time, will be what? Will be, because for this to be 1, in order for this to be 1, both have to be 1, but not that both are 1, because this is 0, it will be 0, and the denotation of phi or xi will now be 1, because in order for this to be 1, at least 1 should be 1, and at least 1 is 1, right, phi is 1, therefore, it will be 1. What about phi implies xi? 1 0 always gives 0 when it comes to this sign. It is because 1 0 means this is happening while this is not happening. That means this is not possible. The if then relation does not hold between two such things. Therefore, this is 0. And then finally we have both side implication or equivalence, which means nothing but it will be 0. It is because, as we have seen, that this means that phi implies xi and xi implies phi with respect to mg. In order for this to be 1, both this and this has to be 1. Since that is not the case, we know that phi implies xi. We have already seen that phi implies xi is 0. Because it is 1, it is 0, and will give it 0. So, that is the reason this is 0. We understand this. So, this is all fine, but then we arrive at the problem. The problem that is associated with the variable. We need to talk about the syntax of it first, then we will talk about the semantics of it. So, we need to erase just part of it so that we have some space for it. Okay. So, the rule I will read first, the rules, rule 8 and rule 9. So, rule 8 is if phi is a formula and u is a variable, then the denotation of all u phi with respect to m and g is 1 if and only if for every value assignment g prime such that g prime is exactly like g except possibly for the individual assigned to u by g prime. The denotation of phi with respect to m and g is 1. It sounds slightly complicated, but it need not be so complicated. Its understanding is not as complicated as it seems as of now. What does it mean? It means something like this. G, we haven't talked about G. Okay, first we will read the two rules and then we will try to understand the meaning. We will see, we also need both the functions g and f. Now, if phi is a formula and u a variable, then the denotation of some u phi with respect to mg is 1. We are reading this rule if and only if for some value assignment g prime such that g prime is exactly like g except possibly for the individual assigned to u by g prime, the denotation of phi with respect to m and g is 1. Now, we need to understand these two things. Then we get back to the section 2, 3, 4. We need to understand the model we are working on, because all the truths or falsities depend on that model. Here is a description of the model. Now, you remember that the model consists of two things. The model has two functions. It consists of two things. I will tell you why the model does not include g. G is something very important, but g is neither included in the language nor in the model. We will talk about it. We need to talk about this, the philosophy of it also, but first the model construction. The model M is a pair A and F, where A is the set A, B, C, saying that in our reality there are just three things A, B and C. So, the model construction is actually very beautiful. Think of it. So, there is one subject, one language user, whatever you call him or her, and then it has got this subject has got a language. I need to correct the head of this thing. So, then So the subject is endowed with kind of a language. What is the language? It's a very simple language. The language we are calling this L1 as of now. The language has got names D, N, J, M. Also, it has two 1 plus predicates M and B. It has two plus predicates. So these are predicates. We are listing them together, L and K, and it has variables like X, Y, Z, and many others. So this is the language part. So and also it has two quantifiers, and it has the brackets. It has all these things. I am not listing all, but you understand. So this is the language part, and it is endowed with this, but then also there is a reality out there. So there are trees and houses, and there are hills and roads and everything, and at the same time it has individuals, like it has people, right? This is very important. So this is we are talking about the reality, the really real, what happens to the really real. But in this simple model we don't have hills and all that. In the simple model we just have 4 individuals, and that's it. So these are not very important. If we want, we can have all these things, but actually this has 4 individuals, and they are these 4, right? They are just these 4, whatever. They have names. The names are D, N, J, and M, but actually 2 of them are the same people. Say, for example, like that is how this is constructed. So it consists, the reality, if you have this as your reality, it consists of 3 things: A, B, and C. A and D. A is one person. They have A has 2 names. One is, perhaps I need to see the construction. Yes, A has 2 names, J and, so the names are J and M. So yeah, A is connected with these 2 names, J and M. And then you have B and you have C. So you call B D, you call B D, and you call C N. So their names are D and N. They are not D and N, they are A, B, and C. So so imagine or pretend or whatever, assume that they are real individuals. A, B, and C are real individuals that are part of the reality, and then they have various relations, right? So for example, if you interpret M, you don't have to, but if you interpret M as man, then all 3 A, B, C are men. They're all men, and among them B and T are bad, which is impossible. So we just reinterpret B as bald person, So then B and C are bald, and then the K part of it. K is a 2 plus predicate saying that A knows A. So if K has to be interpreted as know, then A knows himself, and A knows B, that is, this thing knows this thing, K, and also B knows C. B knows C. It doesn't mean C knows B, but B knows C. This is how the relations are understood. So relations are sets of ordered pairs, right? So, the problem is the model is all about A and F. What does it mean? The model has A, which is the set. So, the model has A, B and C, and it has F. What does F do? F takes the linguistic entities from this box, and so this is the work of F. F takes linguistic entities from this box. So, suppose N, and then relates N. You know that N means C to this. This is the work of N. N takes M and relates this to the set, that is all three, the set of all three, and then F takes L and then relates that to a relation that is held between AC. So, AC, they are related this way through L, and then BA, that is they are also related this way, that is L, saying that B likes A and stuff like that. So, the set of all these arrows, all these relations, then will be L. So, the problem is the model consists of A and F. F is the interpretative function which takes the linguistic elements and interprets, rather relates those to some elements of the reality, but the function G we talked about figures neither here nor there. That is the trouble, and there comes also the beauty of the system we are talking about. Why is it so beautiful? Simply because G is an intermediate thing which exists nowhere. It is a real mathematical entity that is not part of your language, and at the same time that is not part of your reality, that is outside both, but still you require it for calculation, for computation, for several other things. You need G. So, that is the reason, although it is something, although it looks like an element of your system, it is an element of your system, it does not figure either in the language part, it figures neither in the language part nor in the reality part, right. We will see then what it does, which is very important. Okay. So, so we go to the next slide. G is this is our initial G. G has many varieties, every variety of G is a G prime rather, but G prime has got a starting point, that is this, which assigns C to X, B to Y, A to Z. Look, it is a random thing, it could be something else, but we have chosen this G. It does not matter what we choose, we shall see that it does not matter, it could be anything. What is G prime? If you remember, the definition of G prime is this. The definition of G prime is value assignment G prime such that G prime is exactly like G except possibly, very important word, except possibly for the individual assigned to you by G prime. Now, the meaning is something like this. We need this page. So, the initial G looks like this. X gets C, Y gets B, and Z gets A. This is the initial G. One value assignment, one certain G prime, then G itself. When you are considering, so there are three variables we have, right, X, Y and Z. So, when we actively consider some variable, so variables, this is one very important thing, not that every variable looking thing is a variable. Sometimes X may occur, but X may not behave like a variable. In that case, we call it a pseudo variable, but sometimes it is a real variable. A variable is something that varies, right. We shall see that varying part of it. How does it vary? Now, G is something that makes the variable vary. For example, there are all these things, right, but then suppose we shall talk about the 2 plus predicates and all that stuff later. So, as I was trying to say, when you have something like mx, this is a real variable because it varies. It is just a placeholder where other things can come. Does it have its own meaning? No. It means x is m. Is it true? No. Is it false? No. That is the reason mx is not a sentence. It is not a preposition, although it is a formula. It is a well constructed thing, well constructed element of our system, but it cannot have a truth value, right. But the moment I say sum x mx, remember m may be interpreted as a man, it means there exists an m. Here it has got a meaning, and it is actually true because there exists at least one man. There are many men, but it is true that there exists at least one man. You see, this x and this x are not the same thing. This is an x that varies. This is an x which works like a placeholder, but this is not. This is no placeholder. This is a fixed thing, but it makes sense in many different ways. Not they're unrelated, they're related, but this is a real variable, this is a pseudo variable, this is a pseudo variable, while this is a real variable. This is something we need to understand. So that something which varies. Now what varies? We'll see that. The varying variable is parametric. Parametric means here is a variable which is varying. The non-varying variable is just sitting there for several other purposes. We don't know, but we need the varying variable. So, not that we will see that not that every variable is important every time. Now consider just mx as we said. How do I know the meaning of it? Mx without any other quantifier has to collect some kind of a meaning with respect to m and g. So, m is important because the structure of this m, they are different m's. This is the predicate m and this is the model m. So, the predicate m has got a meaning only in the model m. So, it collects its meaning from the model m. That is the reason it is whatever, true or false, or it is working, it is functioning on the basis of the model. That is the reason m is given. But then what about this x? How does x collect its meaning? X collects its meaning from g itself. Now you see x gets c. So practically it means something. With respect to g it means something. Now this is very interesting. This is meaningless. Meaningless in the sense it means something, but this is neither true nor false. This construction is neither true nor false. But the moment I add g here, it is either true or false, because now x has got a meaning. What is it? X will now be c. So basically it means the denotation of m with respect to m g, because if the bases are not the same, we cannot calculate anything. That is the reason we need the base, which takes the denotation of x as a function and x with respect to m and g. And we know the denotation of m from the model. This is the denotation of m, a, b, c, all three, right? We get back. Then it is basically, so functionally speaking, it is a1, b1, c1, and then this gives us c. What is the result? 1. Thus, we compute the truth value of mx, but not mx with respect to the model m. mx with respect to the model and a value assignment function g, without which mx is actually truth valueless. So, if x is a real variable, then if x is parametric, then it collects its denotation directly from g, because g will definitely give a value to it. But then g, apart from giving values to variables, has got another function, changing values, which is very important. There are different g's. So, the initial g looks like this. Then what is g prime? You consider the relevant varying variable, the active variable. With respect to that, suppose we are talking about mx. So, our active variable or the varying real variable is x. In this case, what is happening is, whenever we compute, whenever we talk about it, you see g1 g prime. So, g prime is such that g prime is exactly like g except possibly, that is, it need not be different from g. It may also be g itself, but it may also vary. It may vary in terms of just one thing, only in terms of the active variable x, right. So, g prime, our first g prime can be g itself, which is x gets c. Others, because others are not relevant, we are not listing others. And so, this is basically g. And then second g prime could be, so if this is g prime 1, which is g itself, g prime 2 could be x gets b, others remain the same. You see here, it is possibly different, it is exactly like g, because these all other things remain the same, but when it comes to the active variable x, it changes. So, is exactly like g except possibly for the individual assigned to u by g prime, u here. So, u is our x in this case, u is the active variable. When it comes to the active variable, it is b. Now, g prime 3 could then be x gets a. There are 3 individuals, others remain the same. Now, here we can have only 3 g primes in this case, g prime 1, which is nothing but g, which is possibly different from g, but not necessarily different. The second one is really different from g, but only in terms of one thing, that is the active variable, the variable under consideration x. In the third one, we see that it becomes a, because there are 3 individuals, we have 3 different g primes, because what else will it vary? Remember, we are not varying other variables, we are varying just x, because that is the active variable. This is very important to remember. Now, in light of this, we shall try to understand, we shall try to compute rather the truth value of one sentence, that is all x mx. So, if you want to interpret it, you will say that everything is a man in this. If you put it that way, everything is a man in this system. So, what is the sentence? It is all x mx. We compute its truth value with respect to m and g. Remember, this is our initial g. We are not changing our reference point. The initial g is a reference point. What is it? Now, it is 1. We are following this rule, that is 8. It is 1 if and only if for every value assignment g prime, there are 3 value assignments g prime. Every value assignment g prime such that g prime is exactly like g except possibly for the individual assigned to you by g prime, phi, that is the denotation of phi here with respect to m and g is 1. Now, that means now, so this is phi and this is u right. This construction then is all u, and this construction is phi, right. So, mx is phi. So, if we compare this form, we find this. So, now what does it state? It states that in this case, this is 1 if and only if phi with what is our phi? Phi is nothing but mx. If and only if mx is 1 with respect to all g primes. So, we check it, we check all our cases. This is our first checking case. Our first variant is g prime 1, which is g itself, m g prime 1. Now, you see it assigns, like g, it assigns c to x. What is it? If and only if this is 1 and mx g prime 2 is 1 and c mx m g prime 3 is 1, right. Now, we shall see whether all these, so because there is an AND, we must satisfy each condition, that is A, B and C. We shall see whether all these conditions can be satisfied, or rather are satisfied. Now, we shall check. So, in this, so g prime 1 gives c to x. So, here it will be m with respect to m g, which takes actually the meaning of, because directly it gets the meaning, we do not have any problems, we just directly write. We just directly write c. Is it 1? We check every time. Yes, m c is there in m. Therefore, it is 1. So, actually this is 1, right. This is a checking. This is just, we are checking whether this is the case informally. Yes, this is the case. We go to the second, that is the second one. This assigns b to x. So, it means m x with respect to m g prime 2. Now, this means that mg takes what is the value? B. G prime 2 gives b to our variable x, and since everything is part of it, you see, even b is part of it, c also is part of it, we have seen that. Because of that, this is also 1. So, this is once again the second checking case, and the third checking case, that is m with respect to mg gets, now it is a, this is g prime 3, this also is 1. Since all the 3 conditions, so that's once again checking. So, since all 3 are fulfilled, we must say that the value of this therefore is actually 1. So, we have just seen one rule, and we have computed something, the truth value of something by using this rule. We shall see other rules in the next session. Thank you.